Hey everyone, and welcome back to the Forge College Engineering Lab. I'm super excited you're here for today's explainer, which is titled Guided Translations of Core Patterns. Now, if you've been following along, this is actually part of our capstone on developing a Solidity to Rust/Anchor code pattern catalog, which falls right into our broader From Solidity to Rust and Anchor module, which is all part of the massive From EVM to SVM transitioning from Ethereum to Solana track. It's a bit of a mouthful, I know. But today, we're dusting off some old Ethereum virtual machine blueprints, breaking out the technical pens, and, fingers crossed without spilling any coffee, drafting highly precise Rust and Anchor blueprints for the Solana virtual machine. If you joined our previous lesson on defining translation rules and priorities, you know exactly why we're doing this. So if you've been wondering how to literally translate the exact mechanisms of your favorite Solidity smart contracts over to Solana, well, you are in exactly the right place.
All right, let's take a quick look at our workbench agenda for today. First, we'll review our translation workflow. Then we dive into Blueprint A, which is the Ownable pattern. After that, Blueprint B covering mappings, and Blueprint C for events and errors. Finally, we'll wrap up with a quality assurance checklist. Let's get to it.
Starting off with Section 1, Translation Workflow. Specifically, the three-step process.
Whenever you're turning a compact Solidity original into an idiomatic Rust and Anchor catalog entry, you absolutely must follow this strict three-step process. Step 1. Identify the mapping rule. Basically, ask yourself, what is this EVM state actually trying to accomplish? Step 2. Scaffold the Anchor account. Remember, in Solana, data lives in accounts, not inside the execution logic itself. It's a huge paradigm shift. And Step 3. Convert the logic and add your checks. Honestly, if you skip even one of these steps, well, your smart contract won't just fail, it's going to spectacularly combust. And nobody wants that.
Moving right along to Section 2, let's look at Blueprint A. This is the Ownable pattern, which is basically like handing over the master key.
Now, what's really fascinating here is the architectural difference. On the Ethereum side, Solidity relies on a functional modifier, specifically the only owner modifier for access control. It wraps the function logic. But Anchor handles this entirely differently. We actually enforce this right at the data structure level inside the config struct using a macro. We aren't waiting for the function to execute to check if you're the boss. We check the blueprint of the data itself before anything happens.
And that magic little macro is called the has-one constraint. Anchor uses this to guarantee that the person trying to use the master key is literally the actual owner, well before the logic even thinks about running. Think of it like an incredibly strict building inspector standing right at the front door. By enforcing access control at the deserialization layer, it ensures the signer matches the stored owner. Before a single line of your operational code executes, it's just vastly more secure by design. Which brings us to our official catalog rationale for this pattern. We use a config account initialized at deployment to replicate that single slot EVM state. See, in Ethereum, that owner variable is just chilling in a storage slot on the contract. But over in Solana, because programs are stateless, we literally have to map that single slot state to a dedicated program-owned account that has a fixed identity. It's a completely different way of thinking about state. All right, on to Section 3, Blueprint B, dealing with mapping state. I like to call this one individual safety deposit boxes. So instead of throwing everyone's balances into one giant EVM vault, we shift models completely. A classic Solidity mapping acts like one massive, sparse cryptographic dictionary. But Anchor says, nope, we need you to allocate a distinct user balance account layout for every single user's balance. It's a fundamental shift from a single monolithic ledger to a distributed, massive set of individual files. But you might be wondering, how on earth do we manage thousands of these individual files without losing track of them? Well, enter the PDA, or Program-Derived Address. These individual safety deposit boxes are managed using PDAs, which perfectly mirror the sparse storage semantics you're used to with a Solidity mapping. PDAs are absolutely brilliant because they let the program sign for these accounts using a predictable seed, like, say, the user's wallet address. That means we can securely represent per-address data without needing a separate private key for every single box. Pretty cool, right? The rationale we document here highlights a really key trade-off for your code catalog. We essentially accept higher rent and slightly more complex account count management in exchange for preserving that sparse, per-user storage model. Yes, asking Solana to open an individual account for every single user costs a tiny bit of rent, but the payoff? It parallelizes perfectly. And that parallelism is exactly how Solana achieves those blazing fast transaction speeds.
Let's keep the momentum going. Section 4, Blueprint C, Events and Errors. Think of these as your system's alarm systems and logbooks.
Notice how Anchor's macros provide this incredibly clear, structured mapping from Solidity's raw events and reverts directly over to Rust's result-based error types. While Solidity gives you raw events and custom reverts, Anchor utilizes the event and error_code macros to neatly package everything up into an enum. It practically forces you to handle your errors properly instead of just arbitrarily throwing generic reverts all over the place.
We write this rationale to emphasize a very specific design choice. While we might trade away some of that compact on-chain EVM logging, we gain highly structured event types that off-chain consumers, like your front-end application or a data indexer, can parse with absolute ease. Better observability means happier front-end developers, and honestly, I think we can all agree that is a massive win for the whole team.
Finally, Section 5, Quality Assurance. It's time to put on our hard hats and verify these blueprints.
So what does good actually look like in our engineering lab? Well, first, you run your build command and you want absolutely zero compile errors from the famously strict Rust borrow checker. Second, your catalog entries must be fully fleshed out with the Solidity code, the Anchor code, and your written rationale. And finally, your local unit tests absolutely must pass. You hit all three of those marks and your blueprint is officially ready for production.
Now let's be real for a second. If your build fails on the first try, do not panic. Seriously, the Rust borrow checker just loves to humble us. If you hit a wall, verify your system parameters and double-check your Anchor version flags in your cargo file. Oh, and here's a great pro tip. Temporarily shrink your account sizes to bypass rent exemption errors while you're just testing the underlying logic. You can always optimize the byte size once you know the math actually works.
And that brings us to the conclusion and next steps. We've successfully engineered 3 localized catalog-ready translations today. We mapped ownership, we restructured sparse mappings into PDAs, and we organized our events into strongly typed enums.
Before we wrap up this Forge College Explainer, I want to leave you with something to think about. How will these fundamental changes in data storage and access control alter the ultimate architecture of your next decentralized application? It's a massive question, and it's definitely worth pondering as you prepare for our next topic on documenting design decisions. Remember to visit the website, forge.college, to learn more about this subject, access these templates, and dive much deeper into other Web3-related topics. Keep building, keep learning, and I will see you in the next explainer.